As we said, we have the history or the record of an earthquakes. First of all, we felt about the P wave, that's the fastest one. Or true, we have part of second or seconds between them. Okay? The S wave, then the surface wave, when it will reach, it will cause the damage. Okay? How many earthquakes happen during a year? Is it 10, 100, 2000? We have, as a scale of 2, about 1 million earthquakes per year. Every year, because all the tectonic plates, they are moving, okay? And all over the world, we have so many earthquakes. But these are very small earthquakes that may, because it's about 1 million. We have maybe, if we go to 1 to 8, maybe 1 per year, 1 major, okay? That will cause more than 8. Between 6 and 7, maybe we will have 18 ones. Okay? The major earthquakes, we are in Chile in 1960, it was a major one. Okay? It was 9 points, and this may be one of the highest earthquakes that in the, let's say, previous history that is recorded that hit the earth. Okay? Now, let's go to Lebanon. Okay. We are in the Arabian tectonic plates. Okay. Let's say in the past 200 years, 100 damaging earthquakes, okay, hit this part, and it will cause that it ruins all of the castles of Roman and Ottoman castles in Libya, Syria, and Jordan. The Arabian plates moves, okay, in a circular motion clockwise to the northeast, okay? That will cause earthquakes, maybe we'll see later more about it, to 6, the highest one, it's about 6 points, not more than this, okay? And the Red Sea is due to earthquakes, and it's going to be wide per year, 4 to 6 millimeter each year. Bahr al-Ahmar is going wider. Every year, some records said 1 centimeter per year. Okay? At this part, there is no major earthquake because even it's moving, but it's moving as a divergent one, so it will not cause earthquakes. So it's 4 to 6 meter every 1,000 years. Okay? Right. What are the faults in Lebanon? Let's see in Lebanon. This is the Arabian plates, and this is the African plates. Okay? And this is the Anatolian plates. We have a fault that comes from the Red Sea, okay, passing by Sinai, goes from the Dead Sea, and comes to Lebanon, and went to Syria, and it's a transform fault. And it moves as a strike slip like this. It's not convergent nor divergent. And it's not connected to the faults from the Anatolians. This is where the earthquakes happen. Our fault is not connected to the fault of the Anatolians, where the last earthquake happened. They are separate. Okay? And also we have a fault. They are close to the sea. Okay? This fault, okay, offshore, this will cause an earthquake in 551 that caused that tsunami that destroyed Beirut. This one, because it's in the sea. It caused in 551 a major earthquake with 7.2. This one that destroyed Beirut due to tsunami. When you have a fault, we have let's say, this one. This is the fault that passing from the start to the end of Lebanon. This is the Yamuna fault. Okay, This is the Yamuna faults. And if you can see from the map, you will see that the mountain of Lebanon, it seems that they are one pulse previously. And due to this faults, okay, and earthquakes, they become two, and the Bekaa Valley, okay, is due to this movement, okay, due to the faults, to the Yamuna faults. We have another faults, Yamuna faults. We have an earthquakes happened 7.5 in 1262. In 1262 كان في عندنا major earthquakes 7 points, okay, and maybe it's not this one, another one that destroyed Baalbek Castle. It's 1870s. We have room faults here, room faults at the spots. Okay, this is maybe the closest one to Beirut. Okay, this one, the largest one hit the room fault is in 1837, 7.1. And we have Sergaya faults also that passes by from Lebanon to Syria. We have Sergaya fault, SF. These are the main faults, the Yamuna faults. Okay, and we have the room faults and Sergaya, and we have the offshore faults, and there's electric branches from these faults only. That hits Lebanon. This is another one that shows the faults. You'll see that there's on the offshore there's small cracks in the crust close to Lebanon. This caused that in 2013, a French scientific research increased or upgrade the zone of Lebanon from what we call 2 to 2B. We'll talk about it also later. If we can see also how these plates are moving. So the Arabian plates are moving in this direction, and the African plates also. And you have the Anatolian plates, and this is the Eurasian plates. So this part, these are convergent, okay? Always this symbol of small triangles over the line, it symbolizes, like this one, that these tectonic plates, they are convergent. They hit each other. So we have 3 plates. When we have an intersection of 3 plates, it's an active zone because the movement is more complicated at the spots. So you will see that this is the Red Sea fault that comes from the Red Sea, passing by the Red Sea and goes to the up, and this is the Arabian plates. This is a map that shows the earthquakes, small one to large one, okay, that's in the region. You will see that it's close, the concentration is close to the line, okay, of the faults. And by the way, if you can see Cyprus and you can see this void, because according to the tectonic plates movement, they said that this part comes from this void. Right. So in Lebanon, we have the room faults. The room fault slip rate is about, let's say, 1 millimeter per year. Okay? And the Yamuna faults, it's about 5 millimeter per year. And the Sergaya faults, it's 1.4 millimeter per year. And most of them, the maximum was between 7.2 to 7.5. Okay, that's it. True for us as civil engineer, as structural engineer, the LibNorm, which is the Lebanese norms, specified Lebanon. As we said, it was 0.2 as Zone B in the year 1997, but they upgraded to Zone 3 to 0.25 second, or 0.25 G as acceleration in 2013. This is a table shows from prehistory, from all the records about the major earthquakes that hit, let's say, the region. And you talk about Lebanon, Jordan, and so on. You'll see that, let's say, in Lebanon, 7 minus 140. هون اللي ببلشوا بيعملوا prediction، بياخذ هدول يبلش بقى بيحطوا ورا بعض، اوكي، وبيشوف what is the next one، اوكي. طيب هيك نجرب مع بعض، نشوف شو بيطلع معنا. اوكي. عندنا بلبنان minus 140 and the 6.8 minus 590. We have 400 years between these two. So Lebanon on is 6.8, 6.3, 19, 130, 7.1, 300. كمان passing about maybe 450 years to a major one. Okay, ب 300 صار في عندنا 2. بعدين بال 550 7.5 in Lebanon. بعدين Lebanon 990. So sometimes it's passing 200, sometimes passing 300, 500 years to the next major earthquakes. بعدين عندنا 7.1 with 1000. بعدين we have 7.5, 1200, okay, 1202, 7.5, okay, in Lebanon. Then we have in Lebanon 7.4, 759, 500 years, okay, 7.4. Okay. Then we have 6.4 with 802. So we have, let's say, a major earthquakes that may hit Lebanon, maybe 300, maybe 500. فلو واحد يمكن بعد شو 200 سنة، الله أعلم. No one can predict when it will be the next major earthquakes. But let's say the problem are in the construction of the buildings, maybe. Okay. These are the faults, and this is the application of the last earthquakes in Gazi Antar that hit Turkey and Syria. Okay. What earthquakes will cause to us? We have direct movement of structures. Okay, so if the structure is designed according to earthquake standards and recommendation, it will be a sustain. It can resist these earthquakes. It will cause ground surface faults. Okay, that will cause problem to the landslides and so on. If it is in the sea, it will cause tidal waves like tsunamis, and we are always afraid of fires and gas explosion and so on. For that, when we design, let's say, nuclear station, when we design fire station, fire safety station, hospitals, we have what we call importance factor to improve the performance of these hazards building during earthquakes. Okay. Okay. So building, when it's exposed to earthquakes, as we said, we have vibration, we have acceleration. So it will cause cracks. Okay? We need that this building, in our design as a structural engineer, that this building, maybe it will crack, but it will not collapse. Okay? So based on that, we have to design the buildings, okay, to be more ductile, to resist more earthquakes. How we can do this? Sure, we have the main elements. That's the traditional way that we need shear walls, we have frames, we have a truss or bracing, okay? And we have the innovation items that will help us in earthquakes. We have, let's say this demonstration when we add bracing, okay, how it will behave, how the building will behave if we add bracing like this, okay, to the structure. Let's see this small one, and we are going to make a movement and this is without bracing, and this one with the bracing. You'll see how adding these small elements, these small grain elements, how it improves the performance of the building during earthquakes. So, let's say our design based on that the building, when it would be exposed to strong shaking, maybe it will crack, but it will not collapse. How we can work on this? We need to be aware that always we need a building with strong columns and weak beams. We didn't mean weak beams that it's weak, it cannot resist, but it's weaker than the columns. So if we have a failure, it will happen in the beam, not in the column. So we don't recommend in our design that we will have strong beams and weak columns, because the failure will be in the columns and we don't have a, let's say, announcement that the building, it could fail. Okay. Also, we have, let's say, 3 new basic technology, okay, to improve the performance of a building due to earthquakes. The first one are seismic dampers. The second one are the base isolation, and you are going to see more detailed one. And the third one are tuned mass dampers. What do you mean by this? The seismic dampers are dampers in place of structural elements such as the element bases. It's like a hydraulic shock absorbers. كيف الأمصورات بالسيارة to absorb the shocks. These dampers will absorb the energy, okay, transferred from the earth to the buildings, okay, that will cause the damage to the structural elements. So these seismic dampers will absorb this energy, okay, absorb the hydraulic fluids, and only little is transmitted above to the chassis of the car. So, like also the same performance will be done to the building. This one of the method. Another one, what we call base isolation devices. Okay? The base isolation, the energy or the vibration comes from the ground to the buildings. So if I can isolate through the foundation between the earth and the buildings, so that this acceleration or this energy will not be transformed to the building, so our building is safe. And maybe most of you will see in Japan they are doing this because they are on an active earthquake zone. So they have, let's say, maybe daily earthquakes, so they live with earthquakes. So they need an improved devices. But these, they cost too much, so they are not maybe worth to